So in this particular lesson, we're going to start kind of one of my favorite topics, and that's talking about static equilibrium. And in static equilibrium, we're talking about a specific condition where an object is both not moving and not rotating. We can think about lots of situations where this condition would be true. For example, if we're building a bridge or a building or any type of structure, usually it's not good to have beams in our bridge moving or rotating, or beams in your building moving or rotating. That's usually a bad thing to have happen. And so we'd want to make sure this condition of static equilibrium is true. Now there are two statements that must be true for static equilibrium, and that's that the sum of all forces equals 0, and the second one is the sum of all torques equals 0. So the sum of all forces equals 0 means that in all three possible components, x, y, and z, all the forces add up to 0. And in torques, in any way you rotate the object, the net torque equals 0 around that axis of rotation. So let's take a look at some example problems. And the first example problem is this one here. And I'm going to take two scales, and I'm going to place them 5 meters apart, and then put a 5 meter long beam that has a mass of 10 kilograms with one end on one scale and the other end on the other scale. Then I'm going to get up on top of the scales, and I have a mass of 70 kilograms, and I'm going to stand 2 meters from the scale that's on your right. What I want to know is, what force does each scale read? Now you might say, well, obviously you find the weight of the beam and the weight of Mr. Inman and divide it by 2, and that's what they both say. But wait a second, the mass is not balanced in this case. So the first step I would do in any one of these problems is to draw a free body diagram, identify the forces and where those forces act. First forces we have at either end are what I'm going to call force R, what the right-hand scale says, and force L, what the left-hand scale says. You have Mr. Inman's weight acting down, that's at 2 meters away from the right-hand side. And then we have force of the beam due to gravity. And the way to deal with force of the beam due to gravity is to put it at the center of mass, which, if this is a uniform beam, happens to be right in the middle of the beam. So there's two statements we could make. One is sum of forces equals 0, and the one is sum of torques equals 0. What sum of forces equals 0 says is FL plus FR equals mass of beam times G plus mass of I, which is, I'm going to use mass of Inman times G. Now, unfortunately, with the sum of forces, we have two unknowns. Now, the second thing that I've done is I've found sum of torques about an axis of rotation, and the axis of rotation that I've picked is at the far right-hand side of the beam. What that means is that force L is creating a counterclockwise torque. Or excuse me, it's actually a clockwise torque. I've reversed the signs that I normally do, but hey, as long as those signs are opposite, it doesn't really matter in this case. So force L times R, which would be 5 meters. The weight of the beam times 2.5 meters, going in the opposite direction. And the weight of Mr. Inman times 2 meters. Now, the torque equation can actually be solved for that force L. Move those other two torques to the right-hand side and divide everything by 5, and you find that the force that the left-hand scale is reading is 323.4 newtons. Now, there's actually one of two techniques I could find the force of the right-hand scale. One would be to set the axis of rotation on the far left and do sum of torques equals 0. That'd be valid. Or the second one would be use sum of forces equals 0. I'm going to use sum of forces equals 0. So I'm going to add the weight of the beam and the weight of Mr. Inman over there, subtract the force that the left-hand scale says, and I get the force on the right-hand scale is 460.6. So in this case it says the right-hand scale is going to read a bigger number than the left-hand scale. That makes sense because I'm standing closer to the right-hand scale than the left-hand scale. One common problem that we see in static equilibrium is a problem like this. A beam that's holding up a crate, and we got a diagram. We're going to find the tension in this cable in the middle of the crate. So like I said, draw a free body diagram. And so those are the three forces that we're interested in here. There's probably some contact force between the beam and the wall, but I'm going to make the contact with the wall my axis of rotation because that makes my life a little bit easier. So what I want to do is find the force caused by tension times L over 2 times the sine of 80. That's a counterclockwise torque. The other two are clockwise torques. Weight of the beam times L over 2 times sine of 50, and weight of the crate times L times sine of 50. Now the reason why those are 50 is if it's making a 40-degree angle with the horizontal, it must make a 50-degree angle with the vertical. First thing to point out is that the length of the beam cancels out. I didn't give you any information about the length of the beam. It happens to work out you don't need to know that anyway. That if this is a 5-meter long beam or a 50-meter long beam, the tension would be the same. So now we can solve for tension. Add those other two forces to the other side. And it looks like multiply by 2 and divide by the sine of 80. And so if you work it out, what you find is that the tension in that cable has to be 15,600 newtons. So another way of working through a problem using static equilibrium. I'm going to have a third problem that we can do, and this is probably one of my favorites to work through. And this is another variation on the beam holding a crate problem, except in this case the beam, instead of being kind of sticking out of a vertical wall, is up off of a floor. And so we have this strut off of a floor. It's holding up a concrete block, which we know the mass, and has a cable that runs over it, and the cable's kind of holding up both the strut and the mass. What we want to do is calculate three things: the tension in the cable, and both the horizontal and vertical components of the force acting on the strut from the hinge. So a few things that are important to define angles. If this angle is a 45-degree angle, the angles over here would also be 45-degree angles. And if this angle is 30 and this one is 45, then that angle must be 15 in there. So to go to work out my net torque equation, torque times length of the beam times sine of 15 degrees minus mgl, and I'm using m for mass of the crate, little mgl over 2, using little m to talk about the mass of the strut, and its weight's going to act halfway up the strut, and that equals 0. Looks like I can cancel the L off. Oh, we'll get to that in a second. Second thing to point out is that the x component of force on the hinge should be equal to just the x component of the tension. And then the y component of the force on the hinge, well, there's three other forces in the y component: y component of the tension, weight of the beam, or weight of the strut, and weight of the mass. So it looks like I need to find tension first, and then I could find both the x and y components of this force. So first thing I'm going to do is divide everything by L. It looks like I can then divide everything by the sine of 15. Well, what I did was I combined some like terms, divide by 15, and you end up with 6,630 newtons is the tension in the cable. From there, I can solve for the x component of this force, t times cosine of 30, 5740. And I can also solve for the y component. It has to be equal to t times sine of 30 plus mg, 5960. And so we've solved for these two forces in a more complicated setup using this idea of rotational or static equilibrium. So let's get a quick overview of static equilibrium. The thing to remember with these problems is set up your equation for torque, set up your equations for force, and hopefully you can cancel out some like terms or solve for one of them, or do something that helps you solve for at least one of the forces in that type of problem.